Well, when you're in high school and your mom makes all your pants for free, whatever time you want, and it's like not included garbage fee. There you go. Because you're fucking handling money. Yes.
My mom didn't make it. Funny though, my food made for me now, but it was never made for me like middle school or high school. Middle school or high school never made me anything. But I live with my grandparents now.
Oh, and they help.
Yeah.
Because you have.
But no, soccer was actually a sport that made us discover that I had a
No, you did very good. Because that's exactly what I was thinking.
Soccer is that one sport that every kid in America plays for like a year when they're little, and then most of them never touch
Well,
it.
if it wasn't for soccer, we would have found it out with mountain bike racing because I had.
It's gonna give you another chicken to
as
have.
well.
That's here's your
The soccer season was before the mountain bike racing season. And then I started going freshman year. So,
Bro, you got a beaver. That's you paid $20 for a chicken and then another $5.
yeah, it was one of those, you know, rip normal rhythms.
I'm very glad I don't have that because like all the sports I actually like are very cardio heavy. Apart from sashing, and that's like the least cardio intensive sport ever.
Is it really even a sport?
Pretty sure it is.
Yes, it is.
But you feel pretty smart now.
In fact, my cousin, he was a mechanical engineer at Bethel University in Tennessee. He's I don't even know why he got a mechanical engineering degree because he's a professional fisherman and he got to go there for free on a fishing scholarship and fish and take flight. That is an actual thing. I kid you not.
Oh my god.
Yeah, and he's a professional bass fisherman now and makes a decent amount of money.
It was terrible.
Yeah. Well, I got surgery, so I'm better.
No, it's just not
I can still
because
do
they
it.
wonder.
It does, like, I still have like abnormal rhythms sometimes, and like my heart will like try to go into its own thing, but I can't anymore.
Do you have a pacemaker?
Pacemaker, although my coachmates thought I did when I came with a heart monitor strapped to my hip. That thing went quite a long way. I broke one of them, dropped one out of a tree, and broke one of the fosters. My highest recorded was
280 BPM?
they told me to reach 300 that I started breaking adults.
I was gonna say, how does your heart not explode?
More.
Yeah.
280 BPM, that's what I'm trying.
It's too fast.
They don't have to.
6 times 40 is 240. I'm terrible at mental math.
But yeah, no, I had some issue with the heart adjusting it like the current in that way.
4.5 beats per second.
So everybody's here.
Almost 5 beats per second. How did your heart not
I completely forgot to take your project one file from OneDrive, so I just took it. Well, 2 minutes ago. Sorry. So now I should be gone now. I apologize. I forgot to take it away on noon. So I took it right a few minutes ago. Anyway, so let's just start with the in-class attendance. Next time, I promise I'm not gonna forget to take your file in 12 minutes.
I don't mind it.
I don't mind it, no, it's fine. Yeah, and I usually stand up at the front and type everything into the PC. And this is a little different.
Right, very good. Nobody's on time attendance today. Which is actually very consistent for this particular section. Because the other section is from 2 o'clock, and then there are always at least like 5 people online. I don't know what's the difference.
We gotta do more. I don't know.
Okay. All right, so let's just double check updates. So I think you're done. Done what? What?
Not the project.
Okay, now, okay. So I have a difficult time even catch up myself. So this is done. You submitted, and then I took it a few minutes ago. Sorry, I completely forgot. I was eating lunch and very difficult to remember those things. So now I walk into the classroom, all of a sudden I realize, wait a minute, there must be something due to that. Oh, that's project, let's just take it now. I just did. Okay, so all the files are gone now. Go ahead, question?
Is your percent error for answers on the project similar to for a homework? Because we were coming up with numbers that were very, very close to like tabulated values, but just off.
Did you check against my code? If my code and your code works kind of same or behave very same way, I guess I have no problem. I guess standard atmospheric value seems to be a little bit off. It's not so much off, but probably not going to be like one-on-one relationship. So since I shared you my code, so this one, STD ATM or satellite, you can, of course, you can use and run and compare against your results. And then if the results very matching up, I guess you did okay. I hope no one tried to kind of start from there, trying to code up from here, because I saw some attempts to kind of convert this STD ATM into task2.mlx and then throw it into garbage and try to erase it. But those are the kind of record I can keep track of it. So don't try anything stupid, because I have all the records of what you did. That's the OneDrive, okay? So suppose if you try to do something really stupid, it's gonna be on the record. Okay, I hope you didn't do it. All right, so I guess that's one way you can kind of double check, okay, your result. I hope you didn't try to start from here, convert it to task 2, and then you realize, oh, this is MLX. No, it's not that. Yeah, I cannot do this. Of course, you can't do this. This is Rive script. It's different from regular script. There's a purpose why I force you to do regular script in group environment. Rive script is not suitable for group environment, period. It is suitable for like a presentation, showing your code inside and how to run and take a look at inside, line by line interpretation. Those are good. But I mean, no one would choose Rive script for group project. That's the dumbest possible. Of course.
Would you like to hear something funny? That's dynamics.
Yeah, that's
That's literally dynamics. Yeah. So.
Too bad.
Yes.
That's a terrible pain, isn't it?
Agreed.
Yes.
Who is going to do something?
Like, we just have to have one person work on it and screen share to the rest of us. Like, no, do that.
Of course.
It's terrible.
Because MLX is not designed for group work, period. It is designed for presentation, showing your code and put the nice fonts and figures and then integrate it within and ready to publish kind of. That's the Rive script. That is the purpose why MATLAB created Rive script. And also actually on top of it, Rive script is designed for symbolic math. Are you using that?
Yep.
Symbolic math is a
Most
big
of us.
reason why you want to go for Rive script. If that is what professor is doing, I support the professor rather. Sorry. Sorry about your inconvenience, but I support professor. If that is what is the purpose. Okay. Symbolic math is the key word. That's where it's coming from. Anyways, I'm not gonna ask you anymore. Deal with that person, you know. Any question?
Yeah, I was just wondering, do we know when we're going to have the instruction sheet for phase 2?
Yeah, it's already up. I did take a look. It's a good question. Phase 2 is coming up right here, right after B3. Okay, so it's not a bad idea. Actually, start looking at the instruction sheet to begin with. Obviously, project phase 2, A and B, once you form your team, you have to do both. I'm not going to allow you to break up in the middle of phase 3 or phase 2, okay? So phase 2 and B, A and B, you have to do it in the same team. So now it's time to form up your team, right? I guess that's another update right here, which is due when? I don't know.
Yeah.
Yeah.
That should be done.
Oh, this should be done. Should I check it?
Go for it.
Let's check it. I can check it. So I have to rock it. Well, check it, rock it. Too bad. Okay. Did you sign up? Well, you can sign up right now frantically. Just log into the computer and stuff. Okay, so you're going to take a look at Canvas. This is section 3 of Vero. Yes. This is you. And the people. Project 2, A and B team. Wait a minute, those people are not signed. Wait a minute. Stephen Bruce, Zoe, yeah, that's fine. Robert, you have to sign up. Where do you want to sign up? I'll sign you up right now. This is full. So you have choices either team 2, 3, or team 5 is only 2 people. How about here?
Can I have the same team?
Yeah,
As 3.
What?
As 3.
Huh?
As 3.
Well, team 5 only had 2 people. Why don't you sign up here?
Because it's the same team.
Only 2 people. Only 2 people.
Fine.
Eh? Fine.
No.
I'm not
no,
forcing you. I'm strongly recommending you. That's all I'm doing.
Okay.
You can still say no.
I strongly recommend Team 3.
Team 3.
Does the rest of Team 3 have a say?
Yes.
Team 3. Team 3. You can say no.
Please no.
Okay.
Team
Can I
3
get
said no.
Team
Sorry.
5?
What? So what's your choice?
5.
Team 5. Team 5. Are you okay? Team 5. Jaden. Jaden says no. Which one? Yeah or no? Yeah. Jaden and Dylan. Dylan is right next to you. How's that? Robert. The guy is right next to you.
Oh.
Do you want it? It's your decision, right? I'm not forcing you. I hope so. 100% your decision, right? Your decision, right? Right. Okay. That's it. Teams formed. I'm going to freeze it right here. No one can change. Team is set. Okay. So good luck. So team of either 4 or 3. Every team is, okay? All right. Those 4 people are actually assigned special task. It could be higher workload. Don't worry about it. They're going to show some results at the very end of the semester. You can now criticize at that moment. Big time. Okay? Any question? All right. So Wednesday coming up. Homework is due Wednesday. Friday coming up. Are you doing it? B1?
Yeah.
B1?
Yeah.
It's a mathematics. Do you have any question about anything in Unit B1? Again, don't hesitate. Okay, if you have any question, please send me text. Okay, Microsoft Teams. Okay. So today today I'm going to cover a very important subject. So stay tuned. Quite important subject. So I'm going to continue working on Unit B2. Last class we talked about streamline. And then today, let's take a look at strain and angular velocity. This is basically, if you include the viscosity, this is the mathematical model you have to handle. Do you like it or you hate it to death? I don't know. Viscosity included. So this is something added on. All of a sudden, your program everything is unsolvable by hand kind of problem. Okay? But the mathematical model needs to be developed to begin with. So if you include the viscosity, of course, you can expect 2 things. One is as this element, originally cubic shape, is going to move the position. Move the position is called the translation. Translate. In other words, moving position, slide over to another position. That's called translation. Right. However, if you include the viscosity, this one also rotate and deform at the same time. Rotation deformation effects comes in. So this is called rotation plus deformation. Am I saying that? Yeah, rotation plus angular deformation. Those 2 combined. So those 2 are coming in because of the viscosity. If we if we do not include viscosity, those two can be completely ignored. Only translation is included. Now, mathematically speaking, this is going to massively simplify your math. So you, of course, desire to go with implicit assumption. But let's for a moment, today especially, we are going to include viscosity. Okay. So how can we employ to sort of how can I express this effect of viscosity-based rotation angular deformation effects? Okay. So you are going to look at this figure. This is a fluid element at time t. This is the fluid element at time t plus delta t. So from t1 to t2, you have time delta t. Delta t is equal to t2 minus t1, okay? Okay? So over this delta t, you're going to not only change your position, at the same time, you're going to rotate and deform your own shape. Originally cubic shape, now it's no longer cubic. Now, interestingly, this is a three-dimensional effect, as you can see. So you are going to resolve one plane at a time. So we are going to take a look at XY plane to begin with. Now, similar thing can be applied for the other two planes, XZ plane and the YZ plane. So this is, again, three-dimensional effects. Be careful about that. Okay? So now, rather than using this space, I'm going to switch over to different whiteboard. I have a special whiteboard for you. It's nothing, just a bigger figure. That's it. Okay? So I have a special whiteboard for you. I just wanted to zoom in. Okay? You already have a figure in your notes. Don't worry about it. So first of all, let's take a look at this zoomed in figure here. Before that, let me begin with definition, okay? So the motion of a fluid element, along a streamline is combination of two things, translation and rotation and angular deformation based viscosity driven deformation and then deformation. Okay, rotation, deformation. So those two are combined. The presence of viscosity causes both rotation and angular deformation, those two. Okay? And the flow field is defined something called rotational flow. Rotational flow. Here we go. If the viscosity within the flow field is ignored, it's called implicit flow. The motion of a fluid element can be simplified only for translation. In other words, this is the original shape, cubic element, just to change its position, slide over. It's called translation only. It's called irrotational flow. So rotational versus irrotational flow, but let's just model today irrotational flow. Okay. Irrotational flow field. This is a mathematical model, okay? Very important. Mathematical model. I bet you hate this, but this is important because this is the method we choose to specify irrotational flow field. Now, irrotational flow field needs to be expressed by something called angular velocity, okay? So let's just define angular velocity. I'm going to use lowercase Greek letter omega, okay? Then I'm going to put the subscript omega z. In other words, angular velocity is, suppose you have an x and y plane. You have a rotation around the z-axis. That's why it's called omega z. This is xy plane angular velocity. Okay? So we are going to take care of each plane at a time, xy plane to begin with, and you can do the similar thing for yz plane and xz plane later. So this is omega z. This is going to be defined by 1/2 of delta theta 1 over delta t plus delta theta 2 over delta t. This is actually a very simple concept if you stop and think about. Angular velocity is basically the average of this angle delta theta 1 happens over the time delta t, angular velocity. This delta theta 2 happens over the time delta t, angular velocity. So this edge and that edge rotates. Let's take an average value of angular velocity of it. So that's why this is 1/2 of delta theta 1 or delta theta 2 divided by delta t. So this is average value of how much this edge and that edge rotates over delta t time. This is called angular velocity. Very simple concept. Okay, go ahead.
So we multiply by 1/2 is an average.
That's what I said. Average, yes. Okay, so this is average of each edge. How much each edge rotates over delta t. Okay. So this is angular velocity in z-axis. In other words, x-y plane. So you are going to develop the similar angular velocity on xz plane. Xz plane is omega y, right? Xz plane is omega y, and then yz plane is omega x. So you have omega x, omega y, omega z. I'm just talking about xy plane right now. So having said that, be careful about that. One of them is negative, right? Because I'm going to take the delta theta in positive and counterclockwise direction. So delta theta 2 here is positive. Delta theta 1 here happens to be negative. One is negative, one is positive. Okay, one is negative, one is positive. Let's be careful about that. That's the sign convention. It's just nothing, just sign convention. So this is negative direction, this is positive direction, okay? So we are going to take average value for those. So now I'm going to switch it to the bigger one. Okay, so I just zoom in. So I'm going to take care of two effects. In other words, viscosity is present in this flow field. If the viscosity is present, what happens here? This is the original cubic element. Okay. However, the velocity here on this edge, are different because of the viscosity. Viscosity creates the velocity variation within the flow field, right? That's what the viscosity is. So this edge A, well, this point A is moving in x direction with velocity u, moving in y direction with velocity v. However, point B only moves in this direction with this velocity u plus du, dy, dy. What is this? This is the first order component of Taylor-series expansion, which is the general variation of velocity in x direction. Okay. So essentially, this point A, this point B are moving different speed. That's why this is going to cause a rotation. Right? It's because of the presence of the viscosity. You have that kind of stuff. This point also moving in y direction with different velocity from here. That's why this is going to cause rotation. And also at the same time, you can say this point originally here, over the time delta t moves to this point. This is the original point, move to this point. This is the original point of point C moving to this point over the time delta t. Because viscosity causes it, but this is something called deformation. In other words, this point is deformed to that point. This point is deformed to that point. So I'm going to, first of all, let's talk about deformation. Deformation is a red font. Okay? So deformation causes this much change of point. Original point is here. This point is moved to this point. This is a deformation. How much deformation did you have? Okay, so deformation, let's say this is original B, this is B prime. So deformation, original location B becomes now B prime. How much deformation do you expect over time delta t? Anybody? It's basically the difference of the velocity here. Velocity here in x direction is u plus du dy dy. Subtract u, that is what? Velocity difference is du dy times dy. Multiply by delta t gets you deformation distance from B to B prime. Is that correct?
Yes.
All right, that's what I'm talking about. And also, how about this point? I keep using red font. This is the original location C. So this is C prime. Okay? So now you're looking at from here to here, deformation this much. Again, deformation. Deformation C to C prime. How much deformation do you expect? Of course, it's a similar thing in y direction, right? So velocity difference is, this is the velocity difference between point C to A. So velocity difference is dB dx multiplied by delta t. This is the deformation distance from C to C prime. Is that correct? Okay. So this is deformation. Are you okay? By the way, one is partial derivative, one is ordinary derivative. Let's be careful about that. This ordinary derivative dy is this much distance. dy, this is dx, this is dx. How come velocity is partial derivative? Anybody? Go ahead.
Because you have to do it in the direction.
Direction, yes, because velocity u is a function of x and y both. So this is a multiple depending variable. That's why you have to differentiate only in y direction, only in x direction. That's why. Okay? So let's be careful. So this is deformation. I'm going to go to second page. Take a look at same figure. Go ahead.
Are
Robert.
U and V both
Huh?
velocities? Are U and V both velocities?
Okay.
Just based on like the
Okay, okay. Basic thing. So what is velocity as a vector? Robert.
axis.
Express the velocity in Cartesian x and y plane. Ui plus bj, right?
Okay.
That's right. So u is the velocity's x direction component. B is the velocity's y direction component. Okay, good. Very basic. Okay. This is xy plane. Be careful. 2D. Okay. So we're going to move on next page. Take a look at same figure. Now I'm going to change it to blue. Now we are going to actually take a look at rotation of edges. It's the same yet different perspective. In other words, this is rotation effect. Rotation. It's not deformation, but the rotation rather. Let's assume this straight edge dy and this straight edge dx remains straight. It only rotates with this small tiny angle. One is minus delta theta 1, one is delta theta 2. So let's think about arc lengths. Do you know arc lengths? Arc lengths. So let's assume that for a moment. So this dy doesn't change its length, it's only rotating. So this is the original location B. This is the location B prime. What is the arc length of this? Arc length. Arc length.
dy
dy delta theta 1.
That's right. dy times angle. That's arc length. Arc length. Arc length is, this is dy times minus
Right.
delta theta 1. Yeah, that's fine. 1 minus. So this is arc length. R times length. We actually assume small angle, no? Let's be careful. It only works only for small angle. Okay, so this is also same thing. This is original location C. So this is C prime. Let's find out this arc length. What is this arc length?
dx delta theta 2.
Dx times delta theta 2. That's right. So those are arc lengths. So we are looking at kind of same thing with two different perspectives. One is a deformation effect. The other one is a rotation effect. Are those equal to each other. So these are the arc lengths B to B prime, C to C prime. So this is deformation from B to B prime, C to C prime, and those equal to each other. Let's just set equal to each other. Okay? So next page. Actually, not the next page. We're going to go back to the original note. Okay? So let me just zoom out a little bit. Take a look at the entire picture here. So I'm talking about, if you zoom out, interestingly, those two looks exactly the same, especially if it's a small angle. So this distance, B to B prime, same thing. One is deformation, one is rotation. Go ahead, question.
Is that a proper assumption that the deformation and the rotation are equal to each other?
In this case, yes, because it's angular velocity. That's fine.
Would you get a different equation if you were to say, well, we're not going to assume that they're equal to each other?
In an exact sense, in a large angle, yeah. One is probably inverse tangent of something. The other one is Dengus times. So yeah, it's not exactly the same thing if it's a large angle and all that. But we are going to, first of all, let's assume small angle. So this thing and that thing is equal to each other, and that's the bottom line assumption here, because we want to simplify. Like I said, it's easier to go for more complicated equation that people hate to use. If that's what you want, I can easily do that in this class, but I know you don't want to, especially for exam 2. Right, okay. Exam 2, I want to make everything simple. So this is my attempt to. Let's derive simple equation. Okay? So this is equal to that. So that means, hey, this is equal to that. And this equal to that. Let's do that. So I'm going to go back to my original note. I'm going to do that. What? Are you okay? Oh my goodness, this is math class, okay? I told you. Am I in aero class? No, this is math class, I'm sorry, as long as unit 3 is concerned. Go ahead, question.
Aren't we looking at a rotational flow field and not irrotational?
This is, sorry, that's a good point. This is rotational, big time, yeah. Irrotational means if you ignore all of those things, irrotational. That's right. Great point. Yeah. This is rotational flow field, big time. Yes, rotational flow. If we ignore all of those today's class, it's called irrotational. Yes. Got it. So therefore, we are going to do this, okay? So let's equate rotational and deformation. Okay, so that's the opposite.
Translational.
Sorry, that's opposite. Deformation and the rotation. Sorry about that. Okay, let's equate deformation and rotation. Effects due to viscosity, both coming from viscosity. So again, coming from the other whiteboard, I'm going to basically say, first of all, the edge dy. Edge dy basically says you have a deformation effect, du dy times dy delta t. This is deformation. This is equal to dy times minus delta theta 1. This is going to simplify delta theta 1. Delta t is equal to, well, of course, you can cancel out this dy and dy, of course, okay? So this is going to give you delta theta 1, delta t is equal to negative du dy. Oh, okay. This is interesting. And then how about the other edge? The edge dx. Similarly, this is going to be dB dx dx delta t is equal to dx times delta theta 2. Now obviously, dx cancels out. Then you are going to have equation like this. Delta theta 2 delta t is equal to dB dx. Huh. So one thing you notice now, can we plug in those two back into this original definition?
There's no reason why you can't.
You can do that. So therefore, angular velocity is angular velocity on xy plane omega z is equal to 1/2 of dB dx minus du dy. Okay. This is important conclusion here in this page. Now, one thing you notice here is what is dB dx? What is du dy? Have you ever heard of that kind of stuff? What is dB dx? What is
Variation
du?
of velocity is
This is the velocity. Velocity is variation in the direction of x. In other words, velocity in y direction component changes at each location of x because of the viscosity. What do you call that? It's called boundary layer. Right. Velocity profile within a boundary layer in x direction. This is in y direction. So viscous flow field, of course, viscosity presents. You are going to have a variation of the velocity in certain direction because boundary layer forms up. Okay. So question is, how much velocity change do you expect to have? We never know. It's a nonlinear function. Okay. And also, if you multiply with the viscosity mu, what do you get? You're going to get the shear stress in each direction. So you are going to develop shear stress in this direction, that direction, this direction. Those are Reynolds shear stress model. So viscous fluid within, you always have a shear stress developed because of the boundary layer formed up. This is going to be a nightmare if you want to do it by hand. Okay? So let's move on to the next page. So those are actually something called boundary layer. Okay? And of course, within the boundary layer, you all know shear stress is developed, right? Okay. And then shear stress developed on the surface, the skin of the surface of airplane is something called skin friction drag. You have to deal with it, okay? So this is angular velocity. Angular velocity is, by the way, three-dimensional. Now we just derived this thing. This is omega z. You can do the similar thing. This is x plane, right? You can do the same thing for omega. This is omega y. This is xz plane. This is omega x. This is yz plane. Okay? So this is three-dimensional. So three-dimensional flow field with viscosity involved is going to be, you have to do fully mathematical analysis of first-order functional differential equation everywhere. How can you do it by hand? It's impossible. You have to have some model. Okay, that's called the turbulence model. Here we go. Welcome to the introduction to turbulence model discussions. AE999. I took it when I was a PhD student. AE999, Advanced Turbulence Modeling. This is the introduction to it. If you want to step into that kind of phrase. I have no clue what was taught in that class. It was almost like a philosophy talk. Somebody came up with this model. This model works very well for this application, but it doesn't work at all for the other. I don't know why. Let's discuss about it. Even professor doesn't know. This is turbulence modeling, the introduction to it. Okay? You're not going to, of course, do it in AE301. But let's simplify it. Have you done like unit B1? Have you seen this expression?
Vorticity.
What's this? What is this? What's this?
Del.
Del cross B. What's del cross B?
Vorticity or curl B.
This is called curl. Curl B, isn't it? So a mathematician came up with the expression of curl B. What is the curl B? This is it. Twice of angular velocity in viscous flow field is expressed by curl B. That's the mathematical expression invented for theory of aerodynamics. Okay? So you have to probably go back in unit B1, take a look at what is curl B. Curl B is twice of omega. This is called vorticity. Okay? So this is called vorticity of flow field. This is 2 times omega. Okay? So this is shorthanded notation to represent viscous effects in 3D flow field. Go ahead.
I just wanted to ask what the symbol was called.
Which one?
The
Which symbol?
for curl
This?
B.
This? This
No,
one?
the symbol for curl B.
Ah,
Yeah,
this.
Squiggly Wiggly.
This is
C.
Zeta?
No,
exact.
that's C.
Lowercase
Zeta
Greek.
one hash.
I hate it. I really use it, but like C or something. Psi or C?
C.
C.
KSI. So
KSI.
the letters KSI. Say that in one, as one
C.
phrase. C. There you go.
C. Greek. Anybody from Greek? Are you Greek?
Yes.
Right? Oh, your origin is Greek.
Full
Greece.
blooded. Yes.
Okay. So yeah, let's ask everything too.
Oh God, don't do that.
C. C or XC? Wow. Okay. Lowercase Greek character.
No wonder he knows so much.
Thanks, Brad.
That's right. But I rarely use it. I always use del cross B curl because this is mathematical expression. Okay. So obviously, if you take a look at once again unit B1 material, there is a definition of del cross B, right?
Yes.
Right, somewhere. So please go ahead, take a look. Yeah, this is like the Cartesian cylindrical curl of a velocity field. This is the mathematical expression, curl B. This actually represents twice of angular velocity called vorticity. Here we go. So now, every single mathematical expression introduced in unit B1 is associated with something physical in flow field. So it's your job to kind of associate with. So those are no longer just the mathematics you have to memorize. No, those actually comes with physical meaning. Okay. So let's just practice those things from now on, little by little. Okay. So obviously this depends on your coordinate system you choose. This is a 3D Cartesian, so this is 3D cylindrical. Cylindrical is polar plus z added. So think about circular cylinder, maybe. Polar coordinate added with z depths is cylindrical coordinate. You guys know the third coordinate system you never use probably if you're aero?
Spherical.
Spherical coordinate system, you probably never use it, but if you're astro track, you always use it. What is that coordinate system all about?
Spheres.
This is horizon. This is Greenwich. No, this is measured from Greenwich. This is measured from equator. Distance to the satellite. That's spherical coordinate. One angle, the other angle, distance. That's called spherical. So that's the coordinate system invented to sort of specify spacecraft location, measured from the core of the planet, planet's core. You know, Star Wars Episode 1, planet's core. You have to go through it with a bongo, a transport. Oh no, you guys don't know?
It's been a
Star
while
Wars
since I've
Episode
seen
1.
Phantom Menace, so I'm not gonna
Yeah,
lie.
yeah. Go ahead, question.
So you have components of U, V, and W in the vorticity equation.
Yeah. UVW.
Does that mean that the, blanking on the word, the viscosity is dependent on the velocity of the flow field, or is
Viscosity is
dependent on the
viscosity is a property which is usually depending only for material. So viscosity of air is viscosity of air. Now the velocity is a three-dimensional vector, right? So in 3D Cartesian, velocity comes up with component in x and y, z direction, u, v, w. Each one of them is
affected by the viscosity.
no, each one of them will be different value at each location because of viscosity. That's what it is. So u is a function of x and y and z. V is a function of x and y and z. W is also x and y and z. If you go take a look at different locations, you have all three different components of velocity at different locations if you include viscosity in the flow field. That's how much confusion, how much complication you're going to introduce by introducing viscosity. This is called rotational flow field. Do you want to deal with it? I can do it. Like I said, it's always easier to deal with more complicated things. So in AE301, we are going to make a big assumption. Irrotational flow. That means, oh my goodness, this is irrotational flow. That means this is the definition of irrotational flow. Vorticity set equal to 0. This is going to simplify your equation huge, a big time. So this is rotational flow field. As you move along the streamline, original shape of like this is rectangular shape of element keeps rotating and deforming all the time. You have to keep track of that kind of shape all the time. Mathematically speaking, it is quite frankly every location you have to keep track of all of those first order partial differential equation all the time. Quite frankly, by hand it's impossible. You have to have computational fluid dynamics, which is very simple computational fluid dynamics, including viscosity laminar flow simulation, is this kind of flow field. Okay, you can never do it by hand, obviously. Okay, now somehow you want to bring it down to more simplified model so that, hey, let's just for a moment ignore that effect. In other words, flow field is irrotational. That means vorticity is 0. Take a curl of a velocity field at any location, it is going to be 0. Irrotational flow. That means flow field is, quite frankly, this kind of flow field. It doesn't rotate, deform, it just slide over. Okay? Okay, so far. Do you want to go with it? Sounds great. Okay. So this is rotational flow field. Now, this is the introduction to ideal or potential flow field. Why do we call this potential flow field? Ideal flow is, first of all, you have to assume something. The big assumption is mathematical assumption called irrotational flow field assumption. Once you assume irrotational, that means irrotational. This is important. This is mathematical simplification, okay, big time, math. You're going to simplify your math. Of course, it's coming from implicit. However, implicit alone is not going to simplify your mathematics. You have to apply this mathematical expression to assume, hey, this is irrotational flow. That is going to open the door for your mathematical analysis of flow field, something called ideal or potential flow field analysis. That is the big subject of Unit B3, B4, and then you're going to go through 2 projects. Project 2A and B is all about ideal flow field analysis, okay? This is 100% pure theory. What do you mean? It's a hand math, okay? Hand math is kind of interesting. In other words, unless math is algebraic, I don't think you can handle by hand, okay? You don't want to deal with nonlinear partial differential equation, okay? So we want to avoid it. That's what it is. So next class, okay, go ahead.
If you scroll up, wouldn't 3 be redundant because irrotational means that it has to be inviscid?
Yeah, that's right. Implicit means you're going to assume viscosity 0, mu equal to 0. This is implicit. Now, irrotational is mathematically you are assuming this is correct. So it's a physically same thing, but the two different assumptions.
Okay.
It sounds redundant, but yeah, we have to kind of list it separately because one is coming with, okay, we are going to take a viscosity zero. The other one is, mathematically speaking, if you take a vorticity of a flow field, it's going to be zero. Okay, so we are going to kind of listing those two. So next class, we are going to kind of step right into circulation theory of aerodynamics. So let's be ready for stepping into theory of aerodynamics, okay, in which this class is all about. Let's stop here today. All right. See you guys on Wednesday.
What?
You just look like you're staring at it.
I'm staring intently.
Oh, yeah. The lab report? Yeah.